we're going to start out with our science critic. He made a 45-minute video criticizing the scientific method. Can you believe that?
The scientific method?
The scientific method, of course. But yeah, anybody's entitled to criticize it, right? The question is whether his criticisms have any validity. So let me set this up so that you can hear in his own words what he said, okay? And give me a second here, and we're ready, almost on our way. Here we go. The questions and issues to be addressed in this rebuttal are: is the universe irrational? Is it possible to observe a wave function? And does quantum mechanics propose the collision of wave functions?
Those are all things that have been observed, though. So are you saying that the universe is irrational? Although, to be fair, one of the things that I haven't heard is colliding wave functions. I have heard of collapsing wave functions and interfering wave functions, but never of colliding wave functions.
Okay, so two issues specifically. One is whether the universe is irrational, and the other one essentially, whether a wave function first can be observed and then whether they can collide. And so let's go with the first one. Here's a rundown, okay? And it goes like this. It's not that the universe is irrational. It's that the explanations people have for how the universe works that are irrational. And there I'm giving you some examples. The warpage of space-time or the geometry of space-time is gravity. That's an irrational statement. You're saying that time has geometry. It's like saying that what's the geometry of love? What's the geometry of intelligence? What's the geometry of consciousness?
The shape of time? Is that what they're asking for?
Well, essentially that's what it is, because the physical interpretation that they're going to give is this bending of the canvas. The canvas represents space and time, and so essentially they're saying that they're warping time, and that's gravity. And it's okay if you want to do math and say, look, time goes slower or faster, that's one issue. But when you give a physical interpretation, you cannot say that time is warped, which is essentially what they have. And then the other is a zero-D black hole. A lot of people are not aware that Chandrasekhar got a Nobel Prize for proving that a black hole is zero-dimensional. It collapses to zero size. And people don't like to hear that. They say, oh, what do you mean zero size? Yeah, that's exactly what Chandrasekhar got his Nobel Prize for. Okay? And so you have an object that is zero size, no volume, lots of mass, which is a concept, in this no volume, no size region, and it makes stars go around and pulls matter in. Yeah, sure. And then the other particles have two places at once. Big Bang creationism, and just an example there: faster than light, tachyons arriving from the future. What is all this? And so it's not that the universe is irrational. It's that these people are giving irrational explanations for how the universe works. The irrationality consists primarily in the movement of concepts. Okay, that's essentially the where the problem is.
Well, just using magic at all. I mean,
not even magic. It's black magic.
Yeah, I mean, even magic can't make one thing be in two places at once. Like, no one understands it. You can't even make a program that makes sense of that. Like, nothing.
No, I guess not, right? Because if you assign a name to one object in your program, I guess
as soon as you have two locations, two objects, like that's basically the definition of two things, is because it has two locations.
Yeah, so these are the things that you got to keep in mind, that they have irrational explanation. The universe, I'm sure, works rationally. I hope it does.
To a certain point, I mean, but it gets weird at the infinitesimal level. When you're at the fundamental level, it gets a little weird, but I guess at some point it kind of has to.
Yeah.
But not that weird.
The way I look at it is Mother Nature, Father Universe, God, devil, the devil, whoever you pray to, they don't know anything about concepts. Okay, we invented all concepts, so they work with objects. All they do is move objects from one place to another every day, primarily atoms. They work at the atomic level. So there's constant motion in the universe of what? Of atoms. That's it. That's all they understand. All these concepts, field, energy, mass, we've invented all that. Mother Nature and Father Universe, they know nothing about all that. They never went, like I like to say, Mother Nature never went to school. She knows nothing about math or arithmetic. Okay? That's us that give, all these relations. Anyways, second issue was whether you can have a wave, whether you can observe, first of all, a wave function, and then whether wave functions can collide. Can they actually collide? I put that in there. And this was what this fellow was criticizing, but he conceded at least that they interfere and that they collapse. And what he didn't understand is that there's no difference between interfere, collide, and collapse, because you're treating the wave function as a physical object in all three cases. That's the issue. Okay, so let's look at, first issue is, can you even observe a wave function? And a wave function is what the second word says. It's a function. And what's a function? It's an equation. It's a number. It's an amount. It's a quantity. So you can't say that a function, that you can observe a function like floating out there in space. That's the issue. And if you can't observe it, first of all, then how can you imagine that it collapses, okay, or interferes with another wave function? I mean, what are we talking about? Is this physics? Is this, we have two wave functions that hit each other, that cross each other? What is this? And so, here the first issue is, how do you observe numbers, floating around, moving, right? You can't do that. How do numbers collapse? What do you mean by a number collapsing? And what they're saying in quantum mechanics is the following. So let's understand this well, so that we truly understand it, okay? They say that the wave function collapses to a point. Why? Because when they take the measurement, they take a measurement at a given spot, at a given point, and they say what happened was that this wave function, which is spread out throughout the universe, all the way to the edge of space-time, suddenly collapses, concentrates all of a sudden to a dot. And that dot is what they're going to call a particle. So let's look at what a particle is. This is from the Wikipedia. An idealization of particles heavily used in, I think they said mathematics, but maybe I was a little too liberal with my wording there, okay? But its defining feature is that it lacks spatial extension. Being dimensionless, it does not take up space. We're talking about nothing. Okay? Why? Because we're talking about a concept. They're talking about a number, a quantity. That's what a particle is. It says a particle is an appropriate representation of any object whenever its size, shape, and structure, physics, are irrelevant in a given context. So they're talking about, first, a wave function. What is a wave function? A bunch of vectors. What is a vector? It's got magnitude and direction. And you have a bunch of these arrows which represent magnitude and direction, and they're moving sideways, perpendicular to those directions, right? They're moving sideways, and suddenly all these vectors, numbers, right? They collapse to what they call a particle, which is what? No spatial volume, no dimensions, they take up no space.
Basically, they're just talking about a location with that stores properties.
Exactly, that they measured. And so, how do numbers physically interfere? Because forget about my colliding. I put the colliding in there. Forget about that if you want. No problem. That's my take. But how do they interfere and how do they collapse? What are we talking about? Are we saying that this equation collapses to a dot? Or a point, a ball, some kind?
What is it that collapse to?
Yeah, so colliding, interfere, and collapse in all three cases, whichever one you want to pick there, is a physical interpretation of what they measure. And this is where the problem comes in. Are we doing math or are we doing physics? If you want to do math, no problem. You measure all you want, give me the quantity, no problem. But when you say that the number collapses to a little ball, now we have a little bit of problem. That's where the problem is, okay? That we have a number collapsing to a ball. Okay, and that's scary.
Well, sometimes, like what you said earlier about the warp space, could you say something like, you can calculate useful things with mathematics as if it were warp space. So you use the calculations for a warped canvas, but once you translate that into real life as a physical mechanism, it gets weird where we would be crushing the bottom of the Earth on the surface of space-time.
Time.
So as an equation, it's useful, but as a physical interpretation, it makes absolutely no sense.
Right, and that's where the problem is. The problem is that the physical interpretations, and when people don't understand that, they say, okay, these people know all that math, they probably know what they're talking about. I don't understand that well, No, the question is they don't have a physical interpretation that you can take to the bank.
They shouldn't even bother is the point.
Really, because a lot of them reject that as philosophy. And they say, well, that's philosophy, that's opinion. That's what the
particle looks like, who cares?
Right, it's like, we don't care about that. We don't give a real physical interpretation. We don't understand how all that works. We don't care about that because we're doing math, and we call that physics. No, physics is what Mother Nature does. You need to explain gravity, you need to explain magnetism, electricity, how the atom works. That's physics. But if you just measure and give me an amount and say this is how fast something is, this is how much it weighs or how much mass it has, now you're talking about numbers.
Yeah, that's just describing.
Yeah, and so you cannot translate that or automatically convert it into physics and say it's a ball that's, weighs space-time downwards or whatever. That's where the problem is. The transition from math to physics. Again, mathematical physics is a contradiction in terms. It's an oxymoron, okay? Because math is math, physics is physics. Never the twain shall meet. Okay, so here's a wave function, just so you see what it looks like, okay, what they're talking about when they say a wave function collapsed, or it interfaced, or it interfered, or collided, or whatever with another wave function. Here it is. That's what it looks like, that worm that you see there, okay? This is a fellow who says that all these particles, they form this wave function, and what are those particles? Well, they're values. So each one of those balls that you see there that form that worm, well, all those balls are also quantities. They're just talking about quantities, and more quantities, and that's what the two axes there are really indicating. This is just two axes and numbers on a Cartesian coordinate system. That's all we're looking at. Okay, so let's look at what really a wave function collapse is. Okay, here it is. Okay, and it's scary stuff. So if you're, this is not authorized for people under 18. So if you're under 18, please leave right now. Okay, this is dangerous stuff. Here it is. Okay, here you have the wave moving before measurement, and then it collapses to a dot. That's a wave function collapse. If you never saw it, well, now you've seen it on this channel. Okay, and so the question is, here you have a bunch of vectors. They're moving transversely with respect to the direction of each one of those vectors that represent magnitude and direction. So they have numbers that are moving. That's what you're staring at. They're represented by these arrows. And suddenly that whole bunch of numbers collapses to a ball.
It knows it's being watched. I never understood how physicists could just accept that as an axiom, like the electrons know they're being watched. That matter reacts differently if there are eyes on it. Like that they just accepted that, like, oh yeah, that happens.
Yeah, it's
in what world?
The physical interpretation is what is scary, because in, what was it, I think 1926, when this was determined by Werner Heisenberg and some of his pals there, Schrodinger and so on, what they did, they figured out things that they could not see. So they had the quantities, they had the measurements, but they could not see what they were measuring. In other words, the reaction was invisible or too swift. So what they did was put particles in there. But initially they started with classical particles because that's what they thought they were, and
Ball.
Classical particles are balls. This is a classical particle here. That's what it looks like. Okay, it's a ball. And then they said, well, it's not really a ball because it's actually another quantity that is at this location. And so, yeah, when you have that situation, you're dealing with quantities, but then the physical interpretation gets lost in translation. That's what happens. And you're saying that a number converts into a particle, because they have to give you a physical interpretation, because that's what the reporter is asking for. He says, well, I don't care about your numbers. I mean, what is it? What's the bottom line? What does this all mean? And the guy says, well, the wave function collapsed. And so, whoa, what is that? Well, the number turned into another number, but it's a pointed number. It's like in that region. Okay. In fact, someone said it great for light. He said, light travels as a wave, but departs and arrives as a particle. That's the definition, or I guess the way of representing light. And what are they saying? Well, they're just saying nonsense. They're saying that departs as a particle, arrives as a particle, but in between it's a wave. So you don't really have balls traveling through the air. That's not the notion that they have. They represent it that way, but you saw it just a minute ago how the worm was made of all those little balls. So they still represent it that way, because how are they going to represent a wave if not with little tiny balls that represent, that whole wavy thingy, right? But then they say it departs as a ball, it arrives as a ball, because that's what you can measure at a point, at a location. In between, it travels or extends as a wave. I mean, like take, for instance, a wave of light, a photon, if you want to see it that way, a wave packet, however you want to see that. Does it travel or does it extend from the Andromeda galaxy, 2.2 million light years away, traveling at the speed of light? That's what the distance is, from there to the Milky Way. So does it extend from there to here, or does it travel? And if it travels, where does the wave begin? Where does the wave end? I mean, is it a little rowboat that's traveling through space without hitting anything? Is that how it is? or does it extend? And if it extends, what is extending? Is it a bunch of vectors?